This lesson deals with waveform symmetries. You can find these notes in the ECE202 ebook in Chapter 13 starting on page 14. Many Fourier coefficients are zero when a periodic waveform has certain types of symmetries. For example, if a waveform has equal area above and below the time axis for a cycle, then the integral over that cycle is zero. And that would make a of 0 equal to 0. Let's take a look at what's called even symmetry. If a waveform has even symmetry, and what this means is that f of minus t is equal to f of t, then b sub n is equal to 0. Now why would that be true? Our definition for f of t is equal to this, and f of minus t is replacing t by minus t. So here's t replaced by minus t, t replaced by minus t. If you recall from trigonometry, the cosine of minus x is equal to the cosine of x. In other words, cosine is an even function. For example, the cosine of minus 45 degrees is the same as the cosine of 45 degrees. The sine is an odd function. In other words, the sine of minus x is minus the sine of x. Go back to our previous line of f of minus t, then we could replace the cosine of minus this argument by just a plus argument. So it's a sub n cosine of 2 pi n f naught t. And then for this term, we'll bring the minus sign out in front. If f of minus t is equal to f of t, then this expression has to equal this expression. And the only way that can occur is if this term is 0, because any value of b sub n other than 0 would make these two equations not equal to each other. So that implies that b sub n is equal to 0. Next, let's take a look at odd symmetry. If a waveform has odd symmetry, and this is where minus f of minus t is equal to f of t, then a of 0 is equal to 0 and a sub n is equal to 0. And why would that be true? Let's take our f of t again, and let's take our f of minus t and multiply it by a minus 1. So I get a minus here, and then a plus sign here. If these two are to be equal to each other, then a of 0 has to equal minus a of 0, and a of n has to equal minus a of n. The only number that works for that is 0. A of 0 and a of n are both equal to 0. Next, let's take a look at half-wave symmetry. If a waveform has half-wave symmetry, and this is where minus f of t minus t0 over 2 is equal to f of t, this is just going to be a shifting of half the period, then all the even harmonics are equal to 0. Now, why would that be true? Well, again, let's take our function f of t from our previous page. Let's replace t by t minus t0 over 2, and then multiply the equation by a minus 1. So we get a minus here, and then we're going to replace t by t minus t0 over 2. And likewise over here, we're going to place t by t minus t0 over 2. Now f0 is equal to 1 over t0. So this is going to cancel with this, and likewise with this, and the 2's are going to cancel. Recall from trig again that the cosine of x minus n pi is equal to minus 1 to the n cosine of x. And for the sine, it's going to be equal to minus 1 to the n sine of x. Applying these identities to our last result, we then have minus a0, the summation from n equals 1 to infinity. Here I have my a sub n times the cosine of x minus n pi, where x is equal to this. So that's going to be equal to minus 1 to the n. I also have a minus sign. And then I have my a sub n times the cosine of x, which is 2 pi n f naught t. And likewise for the second term, I have minus b sub n, and then I have minus 1 to the n, and then the sine of x, which is sine 2 pi n f naught t. For this equation to equal f of t, you scroll back up, I won't do that right now, is that a0 has to equal minus a0. And then this term here would have to equal a sub n, and this term would have to equal b sub n. Now when n is odd, I get minus 1 to an odd number, so I get minus 1 times minus 1 times minus 1, an odd number of times, so that's equal to minus 1. So then a sub n equals a sub n, and likewise for b sub n. But when n is even, say like 2, this becomes a positive number, and so you get a negative. So whenever n is even, I have a minus a sub n and a minus b sub n. For these cases, the value of the a sub n and b sub n must be equal to 0. All we have then are our odd harmonics. In other words, the even harmonics are equal to 0. This is some of the properties of symmetry.